We have today two sessions where the speakers are undergraduate students. No, so it's a pleasure to have. It's the first time that we have two sessions with these conditions where the speakers are young mathematicians. No, almost mathematicians. Okay. So I'm not going to take more time. So if you have some questions to our speakers, you can put them in the chat on or in the Q&A, questions and answers. Okay. So let's start. So the first speaker is Andrei Marais. It's a student from Instituto Superior Técnico, and is going to talk about representations of the Higman-Thompson groups. Okay, go ahead, Andrei.
Okay. Well, first of all, good morning, and thank you very much for the introduction, Professor Casimiro, as well as for the invitation. My name is Andrei Marais. I am currently a second-year undergraduate student of mathematics at the University of Lisbon, and throughout my whole life, really, I've been sort of engaged in mathematics. I've participated in mathematical Olympiads, both national and international, but I'd never really had any sort of experience with proper mathematical research until about 9 months ago, when I first became engaged in the New Talents in Mathematics grant paid for by the Caldas Gulbenkian Foundation, which is sort of, I guess, an entry-level research program for undergraduate students. And so today I'm going to be talking precisely about some of the work I did in regard to that program, which is on representations of the Higman-Thompson groups. But before I even start to define what the Higman-Thompson groups are, I really just want to give some sort of motivation as to why we might be interested in studying these representations. And so the first one is that sometimes in mathematics, when we're studying some sort of algebraic structure, it might be easier to sort of look at it indirectly, so study its action on certain objects. And that is what we do, for instance, when we take what we call the dihedral group, and we study symmetries of polygons, their rotations and reflections, and we interpret that as a group. It gives us a more visual approach to what we're working on. Now, in our case, we're not going to have such a visual approach, but it might still be interesting to study these representations. First of all, for the sake of representation theory itself. These groups are what we call discrete, infinite, but finitely presented groups. And sometimes it's quite difficult to say when two of these representations might be, in fact, the same representation. And that is actually the main aim of our work, is to take a family of representations of Higman-Thompson groups and to try and decide when they are actually the same representation. And there's also some other connections to other areas in mathematics. This project originally came up actually through a link it has with dynamical systems and representations of other algebraic structures. And I originally intended to give sort of a detailed account of how these representations come up from representations of the Kunz algebras. And then I realized that that would probably make the talk too heavy for its own good. And so I've decided that we're just going to try and sort of deconstruct the problem to a point where the problem we're trying to solve sort of becomes actually elementary. And so I'm not actually going to even define what a representation is, but I'm going to say how we can prove that two of those representations are actually the same. And so with that being said, let us now finally define what the Higman-Thompson groups actually are. Or rather, we're actually just going to define the Thompson group. And so what we're going to do is we're going to build a group that whose elements are actually functions. And these are going to be functions with very specific properties. They're going to be piecewise linear functions. So we're going to take linear segments and glue them together, essentially. And they're going to be continuous functions with a continuous inverse from the unit interval into itself. And they're also going to have some other properties which we're going to require. We're going to ask that the slopes of these linear pieces are going to have to be powers of 2. And the points of non-differentiability, which are the points where we sort of glue linear pieces together, are going to have to be what we call dyadic rationals. So they have to be rational numbers that can be written with a denominator, which is a power of 2. And we're going to require that there are at most a finite number of non-differentiability points. And so you can see here that I've written down the expression for an example of an element of the Thompson group. You can see easily that the slopes are all going to be, these are linear segments, obviously, the slopes are all powers of 2, and I guess the points where you glue them together again are going to be dyadic rationals because the denominator is a power of 2. And to the side, I've also plotted this function, and you can easily see that it is a continuous function, and it's obviously going to have continuous inverse as well. Now, during this talk, for the sake of, I guess, simplicity, we're going to restrict ourselves to the Thompson group. But the Hickman-Thompson groups are nothing more than wherever I just said the number 2 during this definition, you take it and replace it by a natural number greater than 1, n. So we're going to require that the slopes are powers of n, and that the points of non-differentiability are n-adic rationals. So rationals with the denominator that is a power of n. And that is the Hickman-Thompson group Fn. But again, for the sake of simplicity, we're going to restrict ourselves to this, I guess, simplest Hickman-Thompson group, which is F2, where slopes are powers of 2, and we're taking the dyadic rationals. Now, if you remember, I said that we're going to study whether or not 2 representations of this group are the same. And so, because what we're going to take is we're going to take a family such that every number in the interval 0, 1 induces a representation. I'm going to touch upon that later as well. But it's going to be useful for us to define an auxiliary equivalence relation over the unit interval itself. So what we're going to do is we're going to consider this function f of x equals 2x modulo 1, where modulo 1 is just you're taking the, I guess, the fractional part of the number. And we're going to define a set which we're going to call the orbit of x for every x in the unit interval. We're going to say that an element y is in the orbit of x if I take x and y, and then I can repeatedly apply function f to both of them, not necessarily the same number of times, and eventually I get to the same number, which is precisely what I've written down here. And this is actually where the connection to dynamical systems actually kicks in. But that's beside the point right now. But we're going to call the orbit of x the set of y's in the unit interval, such that for some natural numbers m and n, when we apply f m times to x and n times to y, we get the same value. And this is going to be I don't know, I hope you can hear me. I think my internet is going to be.
We are listening to you, yeah.
Carry on.
Okay, thank you. Okay, sorry, my apologies. And so this is going to be helpful in the sense that now when we take these family of representations, which for those of you to whom this makes sense are going to be representations of f on the space of square summable sequences over the orbit of x, we're going to get one representation for every number in the interval 0, 1. And so our question now is, when are 2 of these representations, which we're going to denote by tau of x, going to be the same? And so there's actually a very partial answer to this question already from the same 2018 paper where Miguel Barata and Paul Pinto first introduced this family of representations, which tells us that tau of x is equivalent to tau of 1/2 if and only if the orbit of x and the orbit of 1/2 coincide. Now, obviously, the first thing that we're going to try to do is to extend this result to tau of x is equivalent to tau of y if and only if the orbit of x and the orbit of y coincide. But is that really possible? How do we know? Well, the proof for this proposition hinges on a very specific observation that there are elements in the Thompson group whose only fixed point is 0, and also on the fact that 0 is an element in the orbit of 1/2. And, well, it's quite easy to see actually that every element in F is going to have 0 as a fixed point. So there's no way to escape from that. But what we realized is that if we can find an element in F whose only fixed points are 0 and some other value, we can use the similar idea to prove a similar result. And so, well, one quick observation we can make is that the linear pieces of elements of F are going to have this form right here. They're going to be a power of 2 times x plus a dyadic rational. And it is evident when you look at this that the only points which can be fixed points to a function like this are rational values, or in the case of the identity, every value in a given neighborhood of another value. But remember that we want to find a function which only has two fixed points, 0 and another number on the interval 0, 1. So this approach is hopeless for irrational values. But what about the rationals? And this is, okay, so we've reduced our problem to trying to find a function which is an element of the Thompson group, which fixes only 0 and a given rational value. And now is where we can sort of use a neat trick, I think. We can exploit the properties of Euler's Stoichhian function and Euler's theorem as well. I'm not going to define them here or even mention them, but just know that Euler's theorem and Euler's function give us interesting properties in regards to divisibility, and we're going to exploit them to find a linear function which has sort of this expression right here, which is going to fix any given rational q on the unit interval. So up to this point, we've found, I guess, that piece which fixes the rational value on the unit interval, but we still have to prove that there's a function of f or in f which actually only fixes that point and the origin, because we don't know that this linear piece, well, we know that it can be a linear piece of an element in f because the slope is a power of 2, and this number right here will be a dyadic rational because the denominator is a power of 2, and this is going to be an integer as a consequence of Euler's theorem. But how do we know that there's an element in f which actually does what we want? Well, I'm not going to prove it here, but it's actually quite interesting as well, because if you simply take that expression which I just showed and you, I guess, truncate it from above and below at some dyadic rational, you can prove that there's always a way to connect this point to the origin and connect this point to, I guess, the point with coordinates 1, 1 under the same constraints, so that you're using piecewise linear segments with slopes which are powers of 2 and with singularities which are finitely many only at the dyadic rationals. So I'm not going to prove that here, but I can give an idea for how you do this, and that is simply to sort of build a staircase where the length and height of each step are dyadic rationals, and that is based off of the binary representation of the numerator of the point where you truncated the function. So it's, I don't know, it's quite an interesting idea in my opinion. I wouldn't expect it to necessarily work, but it does. And it actually works also in the general case of the Hinman-Thompson groups, which I talked about earlier. Every one of these results actually still works. You have to tweak it a little bit, and you actually have to use Euler's theorem again to make sure that it does work as intended, but it also works in those cases. And so we can therefore prove that given a rational number q on the unit interval, there is a function which fixes only 0 and q, and that such that that function is an element of the Thompson group. And so because of that, I guess, reasoning I mentioned earlier, if we know this, we can prove that, in fact, given a rational q on the unit interval, we can prove that tau of x is equivalent to tau of q, if and only if the orbit of x and the orbit of q coincide. And so this result completely solves the problem in the rational case. I really have no insight so far on the irrational case, but I hope that I can generalize this further. And there's also other generalizations you can do to the Hickman-Thompson groups. You can actually take certain algebraic integers with certain properties instead of just natural numbers, and take functions which are piecewise linear with slopes that are a power of that algebraic integer, and so on. But I suppose that's going to have to I'm going to have to keep that for another time. And that being said, thank you very much for your attention.
Okay, thank you very much, Andrei, for the very good talk. So are there some questions or comments? I don't know if you want to ask something. You can write in the chat if you want. Okay. So Andrei, so this work, as you said, you can do another things, no? Another generalizations of this work, no? work with the prime too, no? But you could pick another prime or another.
Sorry, I'm having some trouble with my internet, but
Okay.
yes, if you can take another number which is not 2, yes.
Okay, so it's another kind of.
Yeah, I don't know if you actually could manage to hear me all the way through, because.
Okay. Okay, so thank you a lot, André. Okay, so let's see. We have 3 minutes, but I can pass to the next speaker, Elizabeth Fino. Hi, Elizabeth is a student from Instituto Superior de Economia e Gestão. Okay, so Elizabeth, you can start.
Okay.
Thank you.
So I'm going to share my screen.
Elizabeth,
Yes.
sorry, before you started, can you please, as Professor Anna mentioned before, explain how it, what was your path through this project that you are working on? We have a couple of minutes, and so we will start your talk only at 10:20. Okay, because some people might come at that time, and so in these 2 minutes, can you please explain us a little bit about your path previously?
Yeah, so just like Andrei, I'm also involved in the same project, so a research initiation project with Caldo School Banking Foundation that has been suggested to me by one of my teachers. And that's how I found my way through to research, because I've never done anything of the sort in college. And yeah, that's pretty much it. And in the last 9 months, I've been studying mathematical finance. I've been focusing primarily on the pricing of options. And I've been pretty much just doing research, because the, how can I say this? Like, the bases I had weren't enough for me to study this properly. So I've been really focusing on understanding the concepts and everything.
The background, no?
Yeah.
Okay.
Because this is a very broad, it's a very broad field. There are a lot of models and a lot of things to learn, and that's what I've been doing.
Do you think it's important for a student to begin doing research, or?
Yeah, I think it really builds our capacity of studying on our own and learning on our own. And it really develops your thinking, because you are reading, many times you are reading articles and books that are not presented the way you're used to. And that's a challenge at first, but it's really useful, and it stretches your brain. So I love it.
Okay, very well. Yes, it's good. Yes. Okay.
So what you are thinking about doing after graduate?
Okay, so I finished my bachelor's degree in mathematics applied to economics and management. I'm now pursuing a master's in finance, because I want to see how the things we study mathematically apply really in practice. And then I think I'm going to come back to the mathematics with that extra knowledge, and I think that's going to make me a better mathematician.
Very good. Okay,
Very
you can start now. Yeah, so it's the time. Okay, thank you.
So you're seeing my slides in full screen, right?
Yeah.
Okay, so hello to anyone who have just joined us. My name is Elizabeth. I am a student at ISEG, Lisbon School of Economics and Management, and as I was saying, I just finished my bachelor's degree in mathematics applied to economics and management. And I have been, over the past 9 months, developing some research in the field of mathematical finance, focusing primarily on the pricing of options. And that's what I'm going to be talking about today. So first of all, I need to explain what an option is. So an option is essentially a contract that gives its buyer the right but not the obligation, and this is very important, the right but not the obligation, to trade a certain asset at a future date for a certain price. It's very general. And this certain price is called the strike price. Therefore, there are two parties involved in this contract. On one hand, we have the writer, who is the person or the entity who is selling the option and who is responsible for ensuring that if the buyer decides that they want to carry out the transaction, that is possible. And for this responsibility, they are going to receive a monetary compensation. On the other side, there is the holder, who is the buyer of the option and who gains this right to trade a certain asset at a certain date for a certain price. And for this right, they are going to pay a price. Now, I'd like to touch on some important distinctions in the field of options. So the first important distinction is between call options and put options. And this is very simple. Call options allow you to buy a certain asset and put options allow you to sell a certain asset. And that's it. Another very important distinction is the distinction between European options and American options. So when an option is a contract, as I was saying, and a contract is valid in a certain interval of time. So let's suppose that our contract is valid between the moment 0 and the moment t capital. When you have a European option, the transaction can only be carried out at moment t capital. So at the expiration date, the buyer of the option looks at the market and they decide if they want to do that transaction, that they have the right to do. As opposed to American options, where the transaction can be carried out at any point during time 0 to time t capital. So during the time that the contract is valid. As you can imagine, European options are generally a little bit easier to model. And so that's more beginner friendly, and that's where I started. And those are the options I'm going to be focusing on today. On the other hand, options are contracts, as I was saying, and to entities between themselves, they can contract whatever they want as long as it's legal. And so we can have exotic options, which are options that are customizable to the needs of the investors. So they don't necessarily fit any of the boxes of American option or European option. And given all of this information, you might now be wondering, okay, but why would I ever buy an option? Why would anyone ever buy an option? And what I can say with regards to that subject is that options are financial instruments that can be used for mitigating risk, meaning that they protect agents against fluctuation in price of assets. Now, to make this a little bit more clear, I'm going to give you a practical example. So let's suppose that I have a factory, and in my factory, I make t-shirts. And for my t-shirts, I need cotton. And let's suppose that nowadays I can buy cotton at 10 euros per kilo. I have no idea if that's reasonable, but let's suppose. And let's also suppose that I have the expectation that in the future, let's say in a year, the price of cotton will rise very much. And I will only be able to buy cotton at 20 euros per kilo. Now, since in a year I will still be needing cottons so that my factory can run, I might be interested in purchasing a call option that allows me to buy in a year a kilo of cotton for instance, 15 euros. So if my prediction turns out to be true, and in fact in a year I have cotton at $20 per kilo, I gain by being able to purchase this cotton at 15 euros per kilo. When I buy a kilo of cotton, I will gain an advantage in relation to the market. This is a reward that I get for exercising my option, that is 5 euros. And this is called the payoff of my option. So as you can see, if we are talking in a European call environment, so in a year, it's the only time where I can buy the cotton at that price. So my reward would be like the 20 euros that's the price in the market. So the ST is the price of the underlying asset at time t. And in this case, we are focusing in a case where we can only buy at time t capital, minus K, that is the strike price. And this payoff is always going to be positive because I have the right, but not the obligation to buy my asset. So if I was completely wrong and in a year cotton is at 12 euros per kilo, I would not exercise my option because why would I ever buy something at 15 that I could go in the market and buy it at 12? And that's the reason why my payoff is always going to be positive. Now that you have the basic concept of options, and specifically from this last example, we can see very well that the payoff of my option is going to depend on the way that the price evolves during my contract. And therefore, the price of my option that is very deeply connected with this payoff is also going to be very dependent on the evolution of the price of the underlying asset. And one very well-known model in finance is the Black-Scholes model. And the way that they model this evolution of the price is using this equation. Now, this parameter mu is called the drift, and this parameter sigma is called the volatility. And volatility is essentially an indicator that tells us how much the price varies or fluctuates. So if it fluctuates a lot, we're going to have a big volatility. Now, I'm going to take a little bit of a detour in case anyone isn't familiar with this kind of notation. So for a moment, let's forget that this term here exists. Let's just focus on this part here. So this means that the derivative of S regarding T equals mu times ST. And this is a very typical differential equation, and its solution is an exponential curve. Now, when we add this term, what we're doing is we're adding a random shock to this solution. So instead of going like this in a deterministic way, we're going to go a little bit up, then a little bit down, and we're going to go around the solution, so to speak. And we might end up with something looking a little bit like this. So now coming back from this little detour. In this setting, it can be derived that the price of a call option at time t is given by this expression, where this R is an interest rate, and this regards the distribution of a standard normal. Now, what I want you to take away from this formula are some important remarks. So first of all, the price of the option does not depend on the drift. It can't be found anywhere in this formula. And so if we were to try to generalize this model, it wouldn't be very interesting to try to generalize this drift parameter. On the other hand, we know that the volatility, sigma, is the only parameter in this formula that is not directly observable. And in this model, a very strong hypothesis is made saying that the volatility is constant. However, when we look at the market data, we can see all the previous transactions. So we can see previously traded options, their price, their maturity, their strike price. And if we plug all of that into this expression, we can then derive the volatility, because that's the only thing that we can't observe from the market data. And when we retrieve the volatility, we are getting the implied volatility. And statistical analysis strongly suggests that this volatility is not a constant. And so that this central hypothesis in the Black-Scholes model is in fact not correct. Because when we look at the market data, and for instance, if we plot the implied volatility against the price, we generally get a curve looking a little bit like this, or a little bit more soft, like a skew. And what this means is that the volatility or the implied volatility of an option tend to increase the further the option is out of the money or in the money. So when the prices are here on the extremes. And so it's clear that the volatility is not a constant. And this led to the rise of some new models that consider volatility that is allowed to vary randomly over time. And that is called stochastic volatility. And one example of these kinds of models is the Eston model, that models the evolution of the price of the underlying asset in a very similar way to the Black-Scholes, except for this part here. So this used to be a constant, and now it is a function of t that is allowed to vary randomly, because it follows this process, and it has this square root to ensure that the volatility is always positive. Here, one important feature of this model is that, okay, when we look at this, W1 and W2 are standard Brownian motions. And if you don't know what that means, you can just think of it as the random forces that are driving the price and the volatility. And they are thought to have correlation rho. Now, under some conditions that I won't be describing because I don't have the time, it can be shown that under this model, the price of an European call option is given by this expression, where P1 and P2 are usually thought as risk neutral probabilities that can be found by solving this problem right here. That looks a little bit complex, but that can be solved. And the important thing here is not the formula itself, but is the effects that including stochastic volatility has on the result. And that's what I'm going to stress now. So first of all, I'd like to point out that in both Heston's and Black-Scholes models, higher variance tends to raise the price of all options. And this makes economic sense because if I have a higher variance, that means that my prices fluctuate a lot more. And so I'm more exposed to this risk and my options become more valuable. Now, coming back to just the Heston model, we can look at it under risk-neutral probabilities. That are basically probabilities that have been adjusted to include risk. And we have this new process for the variance that is very similar to the one we had here, but that has these two new parameters that are set to include lambda. That is a parameter regarding the price of volatility risk. And when we look at the model in this fashion, it brings us some useful insights. First of all, we learned that the variance tends to reverse to a mean of theta star in the long run, and that the speed at which this happens is determined by kappa star. And both of these parameters are influenced by risk of volatility. Now, another interesting concept that we learned is the volatility of the volatility. This can be confusing, but let me take this slowly. So if we are allowing our volatility to vary random over time, that means that my volatility is a random variable. And therefore, it has a certain variance. And the volatility is going to be essentially the square root of that variance. This is not the same sigma as the one in the Black-Scholes model. So forget that for now. So as I was saying, if sigma equals 0, then the volatility of the price of the asset is deterministic. And because we have no variance. And in this case, we have spot returns with a normal distribution. Otherwise, if this parameter is not 0, as it increases, it also increases the kurtosis of spot returns. So the spot returns become more condensed around the mean and have a little bit fatter tails. Another thing that I'd like to point out is that spot returns have asymptotical normal distributions with variance per unit of time given by theta star. And this could be interpreted to mean that the Black-Scholes model would do well in long-term options, since it assumes that spot returns have normal distributions. However, this is misleading because the Black-Scholes still maintains that fundamental flaw of not considering risk of volatility that is incorporated even in the mean theta star by the risk-neutral probabilities. Now, to bring this home to conclude, I'd like to talk a little bit about advantages and disadvantages of stochastic volatility. So in stochastic volatility models like the Heston model, we can represent a large variety of effects such as the kurtosis and other effects that I haven't mentioned that the Black-Scholes could not reflect despite being widely used because it considers that volatility is a constant. However, when we decide to use a stochastic volatility model, we have some difficulties and that's partially why the Black-Scholes is so widely used still in the financial world. Because, for instance, just talking about the Heston model, we have parameters that have to be estimated from market data, and market data can change very quickly. So this would require constant calibration of our model, and that can be very laborious. On the other hand, we would require generally numerical methods to solve the necessary PDEs, such as that expression that I mentioned earlier. And that can also bring some problems. And that was all I had to say today. So thank you for your attention.
Thank you very much, Elizabeth. A very interesting talk. So I have a question from Jen. Jen, you want to ask?
Yes, can you hear me?
Yeah.
Yes.
Yes. So you were talking about the parameters in the stochastic model. My question is, do they only depend on the price on these kind of models or other types of data?
Okay, so we have, for instance, we have this parameter lambda that depends on the volatility of the price. So it kind of depends on the price. And yeah, mostly they depend on the price or on the returns. So not just on the price, but on the environment of the market.
More variables, no?
Okay,
not just...
thank you.
Okay, more questions? Comments? Are there other models for this?
Yeah, There are a lot of models.
Yeah.
And there are also, for instance, these kinds of models, they assume that the price is continuous, so it doesn't jump. And some models have this feature of jumps included in a price, and that's important because sometimes the price jumps when certain news come to the market. So, and there are a lot of models regarding this.
Okay, depending on the situation.
Yeah, because when you have a model, okay, so we have this, and now we test it and we see, okay, but this doesn't include that feature that we happen to observe, and someone comes and does another model, and we repeat this process. So there are a lot of models that are always building on each other and adding new things.
And you have to compare them, no? Sometimes, no, and to see what is the best. The better.
In practice, the Black-Scholes is still very used because it's the easiest one to use. And I don't know, maybe people who work in finance don't find it that important that volatility varies over time. But in some results, we can see that it makes a big difference in the prices.
So it's important not to.
Yeah, mathematically it is.
Okay.
But the Black-Scholes allow us to do some other type of analysis, like sensitivity analysis, that might be harder on other models. I think that's why it's so used.
Okay. So, yeah. Okay, thank you. I don't know.
Thank you, Elizabeth. What do you see yourself doing this in your future, for instance?
Yeah, maybe. I don't know what the future holds, but yeah, I find this very interesting. So that might be an option for me.
Yeah.
That's a stock marking, no.
Market, yeah. It's very interesting.
Okay, so we have 2 minutes more, but I can introduce the next speaker. So thank you a lot, Elizabeth. Now,
thank you for the invitation.
No, you're welcome. Okay, so the next speaker is Jan Markson. Okay, I think, there he is. Okay, so Jan is a student from Instituto Superior de Engenharia de Lisboa. And also he is a member of the Center of Rapid and Sustainable Product Development of the Polytechnic Institute of Leiria also, okay? And he is going to talk about topology optimization, applications in bioscaffold design, okay? So thank you, Jen. Okay, so you can, I think you can start. You can tell us about your path. How did you start with this project?
As Professor Casimir said, I'm a student at ISEL, and at the end of the graduation, we can choose from various projects. It's a type of internship that we do, and we can choose working in a research center or even a company. And the project I chose was to work with CDRSP in topology optimization applied to bioscaffold design. And yeah, this is going to be what I will be talking now. So first off, I'm going to start to explain what are scaffolds and why they are needed. So millions of surgical cases annually require the reconstruction of bone defects in the appendicular skeleton. This can happen because of disease or because of trauma. And there are nowadays 2 types of conventional therapies that are used to treat this kind of problem. One of which is bone grafting. And in bone grafting, you take a little bit of bone from the own patient's body and implant it into the defect site, which is called an autograft, or you can get bone from an animal or another person, and this is called an allograft. This, of course, has the advantage that you're implanting biological tissue, and it permits the implant, so the bone graft, to integrate very well with the host's tissue in the defect site. But it also has the problem that you need a second surgical site, and you also have a limit on the material usage because there's no unlimited bone that you can use for the defect. And sometimes you even have a shape mismatch between the graft and the defect. And this is a big problem. The other type of therapy used very often is synthetic material reconstruction, in which you do not need a second surgical site because you're fabricating a type of structure to be implanted into the defect. And there's no limit on the material when you're not thinking about costs, of course. And you can specifically shape the geometry for the defect. But it also has its shortcomings, such as sometimes the material cannot integrate very well with the host tissue. And if the geometry is filled, then the bone cannot form inside the defect, which is something that is very good in these types of treatments. These problems motivated the third approach, which are the so-called bioscaffolds. The bioscaffolds are types of solids that are biodegradable. They should be very porous, as we can see in this picture. We have a defect, and we implant this bioscaffold. A scaffold in Portuguese is called andaime, which you use in the obras. But here it is a type of structure that should provide a mechanical support for the defect while the bone is regenerating inside it, as we can see in this picture. It has the advantages that it's rapidly manufacturable. We do not have a limit on the material, again, if we do not think about costs, and we can specifically manufacture the shape for the defect and for the patient. But there is a problem, because these structures, they must be very porous, but the more porous the structure is, the less stiff the structure. So we really need to optimize the internal structure of the scaffold such that it is as porous as possible, but at the same time it provides a good mechanical function. This is the work that I've been, this is the type of work that I've been doing. So just to have an idea, the main steps involved in designing a bioscaffold is imaging the patient with a CT or MRI, computed tomography. And then we can get the external shape of the scaffold. And the third step is designing the interior shape of the scaffold. And the goal of this work was to optimize the internal structure of bone, the trabecular structure of bone, such that we can use these results to design the interior architecture of our scaffolds, because they should resemble as much as possible the native bone in the patient. At the fourth step, we joined both of these designs, the exterior design and the interior design, and we converted to a fabrical, a format that can be printable or that we can fabricate using other types of methods in solid freeform fabrication. The step number 3 is done usually nowadays in many types of ways, some of which are salt leaching or repetition of unit cells. We have a unit cell with known properties, and we assemble the repetition of many of these unit cells to create the whole scaffold. But we, of course, have the disadvantage that we do not know that these scaffolds are mechanically optimized against outer stresses that are happening when the patient is doing their daily activities. So my work was to use topology optimization to start working on the design of these internal structures. So the topology optimization is based on this differential equation. We have a solid, a continuum, which has an original configuration. Forces are applied, and it then deforms into another configuration. And this transformation is characterized by a displacement field. And what we want is to solve this differential equation to get this displacement field such that we can optimize the structure as to minimize this displacement. So what we do in practice is not solve these differential equations directly when we're talking about more dimensions. What we do is we convert it into an integral form using the principle of virtual work. And then we interpolate, we discretize our domain in various elements in which we have nodal displacements, and we get the finite element equilibrium equations, which we have to solve in the topology optimization problem. So the problem is we have a domain, and we have forces applied to this domain, and the method should optimize the structure. It should allocate density or material at the specific places where the structure is going to be as stiff as possible. So this is the problem. We want to minimize the elastic energy or compliance such that we minimize the displacement, and we have the conditions that we have to respect a prescribed volume fraction, and we have to respect the equilibrium equations discussed earlier, and our densities. So we have many elements, and each element has a density ranging from 0 to 1, where 0 is no material and 1 is material. And we can see that the stiffness of each element will depend on this density. But these are details that I will not discuss here. But we know how to optimize a structure for our scaffold, but we need our scaffold to be very porous and to have interconnected lattice-like structures, as we can see in these types of pictures. How can we accomplish this? We have our optimization problem, and we add a perimeter constraint. So we want our perimeter to be bigger, such that our structure will have more holes. So if we augment the perimeter, our structure will have less pore area, less pore separation, and more pores, which is what we want for these types of structures. And how do we impose a specific member thickness? Well, we use something called a density or sensitivity filter, which is very commonly used in topology optimization, in which one element will depend on the neighboring elements within a specific radius. And so we can control the thickness of the members of our structure. Well, I've been using Hooke's law to formulate this problem, but it's assumed, we were assuming in this model that our elements are isotropic. This means that their mechanical properties are the same in each direction, which is actually not true for bone when we see bone at a bigger representative volume. So if we see bone at a representative volume of the millimeter scale, we can see that the mechanical properties, they really depend on the trabecular orientations that the structure has. But when we see at the tissue level, we see that the bone tissue can be approximated with isotropic mechanical properties, which is very important in this model assumption that we've been doing here. So here we have a simulation example. I decided to use the example of a human femur, a cross-section of a human femur, such that we can simplify this problem to 2 dimensions before we move on to 3 dimensions. We have a cross-section of a femur with dimensions 100 millimeters by 100 millimeters. We specify all these details that I've been discussing earlier, the trabecular thickness, separation, volume fraction, and then we also prescribe the boundary conditions. So we have a human femur, a cross-section, and we apply the forces that happen during a human gait, the reaction forces happening during a human gait. So these are the forces. I will not go into great detail here. And we apply these properties, and we can see that from an initial configuration, an initial distribution of circles, we then start to see trabecular patterns forming in these areas. Here I have the picture of the final iteration, and we can compare it to a real trabecular bone, and we can see that there are very many similarities. And this suggests that our trabecular bone is functionally adapting to the reaction forces it experiences during our normal daily activities. So our bone is formed as to be optimized, structurally optimized against the outer forces. Here we can see the main compressive and tensile groups, but I will not go into great detail here. We can see that we can compare the volume fraction of certain areas of our simulation with the real results. These type of validations will be done in future work. We can also extend this problem to 3D, as we can see by some pictures here. And now, just to conclude, what our future work will be is to design a optimization framework which not only minimizes the elastic energy as to turn the structure the stiffest possible, but we want to add other types of objective quantities like permeability, such that the cells can differentiate inside the defect easier, and other types of constraints, such as a prescribed value of the Bolt modulus, for example. And we also want to extend this problem to 3D. But the problem here is that these kind of finite element discretizations, they are very huge, and we have systems to be solved by the computer that are with matrices that have millions and millions of entries. And this is one of the main challenges that we have to construct this type of optimization framework. And this was my presentation. Here are some references for someone who can be interested in this topic. Thank you very much.
Okay, thank you, Jan. Very interesting. Okay, are there any questions for Jan? Do you want to ask something? No. Did you apply this this study to real problems in the hospital or something?
Sorry.
Did you apply
Your
this,
internet connection was a little bit, yeah.
Did you apply this study?
What we're thinking of, what we want to do is we want to get a computed tomography of, for example, a sheep or a rat, and then we want to compare the results that we get from that micro CT to the simulations we've been doing. And in the future, what we want to do is we want to make a case study of a defect, and then use the information that we obtain from one simulation to optimize a little part of the bone that should be filled with the scaffold. This is what we really want to do.
Okay.
I don't know if I was very clear.
No.
And maybe I can add also and take the chance until, as we have a couple of minutes also, to mention that yes, this work is a joint work with the Instituto Superior Técnico de Bioengineering and Bioscience, IBB, Institute of Bioengineering and Bioscience in Tagus Parque in Oeiras. And also with the ICBAS in the University of Porto, and with these two partners, what we do is the in vitro and the in vivo tests. So now in this work, in particular the work that Jan is doing, is optimizing these. Is doing this optimization of the femur of the bone. Now it's the femur of a sheep in this case in particular. But what we want is that we next step will be trying to mimic this in our laboratories in CDRSP. We are a research unit from FCT. And so focus in additive manufacturing applications, 3D printing, and so we have developed our own equipments, and we have laboratories where we can print these structured, and then we will test it in either in vitro and also in vivo in the near future. And so this is a joint work that intends to accelerate bone regeneration. And so this will be an opportunity to have to optimize solutions for human patients that deals with the bone fractures, for instance. Let me also mention to our all the participants and the young students that are participating here, that are here with us, that Jan is participating in a FCT project, and so there are a couple of opportunities that you can take. So it's a funded project, is receiving a salary per month to work in this project. this is a scholarship, and so he got the chance to find this scholarship, and so he's doing this great work with us. So yeah, I don't know if you want to share your experience regarding the participation of these projects. You have 2 minutes if you want to.
Yes, it was really great because even though mostly I had to stay home because of COVID, of course, it was very great because I had students also in the center, doctoral students that showed me around the center, and I've got to know great people with very interesting projects. The laboratories that they have there, they have lots of equipment, and there can be many things made and many ideas accomplished in these types of projects. So I really encourage everyone who's listening to join on.
Can I make a question?
Yeah, of course.
A small one.
Yeah. Go on.
Just to clarify, what do you use MATLAB to solve the optimization problem? Do you use MATLAB?
Yes.
What kind of solver do you use in MATLAB?
Well, the topology optimization.
In the previous slide, you have something about that. You have some information. I can. Yes, it was
here. Yes. You mean the solving of the system or the solving of the optimization problem?
No. First, the solving. First, I have 2 questions. That's the second question. First, how to solve the optimization problem.
To solve the optimization problem, initially, before we had more constraints, we directly used the Karush-Tucker conditions to derive an optimality condition, such that it could be iteratively refined. But when we added more constraints, it was not possible anymore because we were using a bisection algorithm and the functions are all very implicit. So we had to use a convex approximation scheme. So at each sub-iteration, we approximated the optimization problem into convex functions.
Yeah. And then
into a convex problem.
What's the solver that you use? Which solver?
The solver that we used was.
You have several solvers that you can use it. To solve.
The solver was directly written by this author, Dr. Christoph Swanberg. Yeah, he was the one who invented this convex approximation scheme, and he wrote a MATLAB code that can solve it. Yeah. And the system.
It's not a general one for every.
It's not a general one. It's very specific for structural optimization problems because they have specific properties. Types of problems have specific properties that make these kind of approximations possible. Yeah.
And to solve the system, you have a very big dimension. You have huge dimensions.
Exactly. At each step. Exactly. At each step, a system must be solved at each iteration.
Yeah.
When we're talking about 2D discretizations, we can still use the Cholesky algorithm, which is very fast. But when we start to make 3D discretizations, we start to have very huge systems. And we cannot do the whole process of the Cholesky decomposition and forward and backward substitution. And we have to move to other types of algorithms, such as iterative ones, like the conjugate gradient method, and variations of these types of methods. Because we then have millions and millions of entries.
You can use directly the composition of the metric of the system because you have a huge dimension. I understand. Yeah. Okay, thank you.
Okay, thank you a lot, Gianna. Okay, so now we are going to the next speaker. Okay, so Rodrigo Joshua.
Good morning.
Hi, Rodrigo. From Minho University, no? Universidade do Minho,
Yes.
okay? And he's going to talk about mobility indicators, okay? So you can start, Rodrigo.
Thank you. So, good morning. I'm Rodrigo, student of Universidade do Minho, and I recently finished my bachelor's degree in applied statistics, and I'm here to present my project/internship done during this second semester of this last year. So I will now start my presentation. Before starting, here's a small index that illustrates what will be portrayed throughout the presentation. It is important to mention that Chapter 4 will only present the results for the Northern region, since there are 7 regions in total, and I would not have time to show them all. The goals were to determine indicators to help analyze mobility of the Portuguese population during a COVID-19 period, from 15 February 2020 to 27 February 2021, and then analyze that mobility based on these indicators that we determined. Before starting, the database used. This database was made available by Google through Google Mobility Reports, where Google collects information through the location feature of Android systems. Only 9 of the 15 variables were needed in this project. The first one was the country region code, which is a little code that identifies the country. The next variable was subregion 1. It shows the districts of the country. The next one was date. It shows the day of the observation. And the last 6 are the mobility in different sectors. It is important to mention that these last 6 variables are in reference to a baseline, and that baseline is the median value for the corresponding day of the week in the 5-week period from January 3rd to February 6th, 2020. Now, the methodologies used. The first one was principal component analysis. It is a multivariate exploratory analysis. Its goal is to summarize information from several variables into a smaller set without losing any kind of significant information. The principal components are linear combinations of the existing variables, as you can see here in the first photo. And they seek to explain the maximum variability of the data. PCA can be used as an assist to other analyses, for example, for cluster and discriminant analysis. Now, how many principal components to retain? Generally, the answer is those necessary for the following conditions to be met, as you can see down here. Now, another methodology, moving averages. They are sequential estimators of the population. Their purpose is to detect trends in the data. They have no kind of predictive ability. They always remain one step behind reality. Of course, it is necessary to adjust the time interval in order to obtain better results, and it is given by the following formula. Now, working with the data, to facilitate the interpretation, data was divided by districts. So 20 tables were created, 1 for each district and 1 for each autonomous region. Then it was analyzed whether the amount of days observed is 379 in each district. And it was found that no, there are some districts with fewer days observed. A little note here, 379 observed days are the days corresponding to the interval mentioned before. It was also analyzed how many of these districts do not contain any kind of missing data. There are then 2 problems that need to be addressed before proceeding. As you can see in the first photo, only 13 out of the 20 districts contain 379 days observed, and only 2 out of 20 contain no missing data of any kind. Now, the problems were needed to be solved, and the first one was solved assigning the same number of observed days to all districts. We found out that Bragança is the district with the fewest days observed, with 373, and so all of the other districts were placed with that same number of days. The second problem, the one with the missing data, was solved in 2 steps. The first one, where we defined the upper limit of 20% in relation to missing data. That means if any variable contains more than 20% of missing data, it will not be counted in the analysis. And so after selecting the variables that will be counted, we move on to the second step, where we input the missing data. We did this selecting a period right before and right after the missing data that we wanted to input, then take the average for each of these periods, and after that take the average of these 2 periods and input this value on the missing data. After solving the problems, we then proceeded to group the districts by region. The regions we used in Portuguese are called Administração Regional Saúde, but I'll call them ARS from now on, just to be more clear. We did this using weighted means, where we sum the multiplication between the variables and the population of the respective districts, and at the end divide that value by the population of the ARS. After grouping the data by ARS, moving averages were created for each variable, of course, and with a time period equals to 7 days prior, in order to try to avoid abnormal values, especially at the weekend. After this, we start to see the first results. The first one we got was the summary of the code used to perform the principal component analysis. It is a table that shows the percentage of variability explained by each principal component and cumulatively. With the first glance, we see that with only the first two principal components, it is already explained about 95% of the variability. But even so, we got some more results to help us understand how many components we should retain. The next result we got was this graphic. It shows the quality of representation of the variables by only the first two principal components. As we can see, they are extremely well represented by only these two principal components. And so it helped us a little bit in the deciding process. Even so, we got another graphic, this one, the correlation plot, where it shows the correlation between the variables and the principal components. It is notable that only the first two principal components show significant correlation with the variables. And so right here, we decided to only keep the first two and get some results, but only with the first two principal components. Then we got this graphic. It represents the relationship between the variables. The first conclusion to draw is that residence is inversely correlated with all of the other variables. That is, if an increase in mobility in this sector will result in a decrease in mobility in all of the others. That's kind of obvious. Another conclusion is that variables associated with leisure are in the second quadrant, and variables associated with work and obligations are in the third quadrant. So with these two conclusions, we can draw the last one and probably the most important. Since residence is related to positive values of the first principal component, it follows that this component will be an indicator of lockdown. And since positive values of the second principal component and are related to leisure, and the negative values to work, this will be an indicator of leisure or mobility. So here's a video I made that shows the evolution of mobility of the Portuguese population in the northern region. It is divided into 8 periods based on measures that were applied over the time. As a video, it helps us have a better perception of the evolution of mobility, since with a static graphic, we can get much of an idea how mobility has evolved. This graphic / video help us to draw really important conclusions about the evolution of the pandemic, and also to understand whether the measures implemented or eased by the responsible entities were effective or not. It also helps us to understand the behavior of the population itself, if we really respected the measures or not. And finally, it help us in better understanding how to act in similar situations in the future, since we already know the effect of some measures applied. The video is just ending. As we can see in the top left corner, we have the date of the observation. So at the end of the video, we get this graphic. It represents the mobility of the population in the region, in the northern region. I think this kind of analysis will be helpful in all countries. A work that I would love to have developed was a similar analysis for other countries and compare it with Portugal. I think it would be really interesting, especially if it was a country with a different position to Portugal in relation to the pandemic. So we could compare and understand what we may have done wrong or well over all this time. So basically, it was my presentation. I would like to thank you very much for this opportunity to show my work developed over past these months. I hope you really liked and understand it, because my English, I know it's not the best.
No, no.
But thank you very much.
Okay, thank you, Rodrigo. Very, very interesting work. Okay, is there any question you want to make? Comment? No. So, yeah, Paula, you want to?
Yes, first, I would like to congratulate also to Rodrigo and mention that his English is very good. So, what is the most important is that your message is able to pass, and so it was we perfectly understood you, and so thank you for your participation. Just would like to your work is very very interesting, and due to this our context right nowadays, this pandemic situation, wondering if you present your work or discuss your results with also virologists, other virologists or medical doctors. You like
also the Prime Minister.
So, I worked with the Institute Ricardo Jorge.
Ah, okay.
So I was always in touch with virologists, and we were always discussing the results, and they really liked it as well.
Okay, very well, very interesting. Yeah. Okay.
Yeah, I've heard, Anna, sorry, you want to, yeah? I know that there's a lot of mathematicians doing an amazing work together with virologists and other medical doctors and so on, and so working together with the government, and that's why there's a lot of decisions that are made based on these models. And so this is very interesting to see where mathematics can goes, and we can see in all these previous presentations, and I'm sure in the next ones and in the afternoon ones, that it's so interesting to see that mathematicians can spread in all areas and contribute, gives an amazing contributions to each field. And congratulations once again, Rodrigo, for your work.
Thank you.
How did you start this work? It's in.
So it was my internship. The last thing we have to do to finish the degree. It's an internship, and I chose to work with the Institute Ricardo Jorge. So we had some meetings, and we concluded this was a really interesting project, working with the mobility. Google really helped us by collecting all of the data. We just had to work on it. So it was really interesting, and maybe I have so much more work to do with this.
And just so you are going to continue to
with
this project? Okay.
Maybe alone if needed, but I really like it. I really wish I can do this kind of analysis to other countries and compare it with Portugal, so we can see the difference of the evolution. Basically, that's it.
Okay.
So are you, sorry, and are you planning to go for a master afterwards?
Yes, in statistics as well.
In statistics.
Yeah.
Okay. So anyone wants to make a question? No? Okay. We're going to wait 5 more minutes. I don't know if you want to go to the bathroom or make a quick, I don't know.
Quick break.
Okay, so, but I can now introduce the next speaker, and we can wait 5 minutes, but we can. So the next speaker is Rodrigo also, but now Rodrigo Pereira. Yeah.
Good morning.
Hi, Rodrigo. Rodrigo is from Faculdade de Ciências from Universidade do Porto. Okay.
Exactly.
Okay, so hi, Rodrigo. Can you tell us a bit about yourself?
Yes, I've just finished my bachelor's degree in mathematics at the University of Porto. Like some of my colleagues, I've also had the opportunity to receive the Gulbenkian grant, the new talents in mathematics. And so that's what allowed me to dip into the world of mathematical research, and it's where this presentation came from.
And you are enjoying it, no?
Yes, it's been. This is actually a last year's project because I thought it was a bit more polished than the one that I'm doing right now. It still needs some more work, so I thought it was a bit better to present that. But yes, I've definitely, it's been a great experience. Both last year and this year's project, and yes, I recommend it to anyone wants to try it.
The other students
for
also,
sure.
to start. No?
Exactly.
Of this project.
So, what you're planning to do now, Rodrigo?
Well, I'm planning to follow what I suppose is the most natural path, which would be pursuing a master's degree. I'm not yet totally decided on where, but I'm thinking about it. Time is there's not much time left, but
okay, but you are.
I'm thinking about it.
There are so many areas, no, to.
Yes, there's so many areas, there's so many places.
So it's difficult, no?
It's not a very easy decision, no.
Okay, so we don't know yet what are you going to do. Okay, but if you can start sharing.
Okay. Well, I hope everyone can.
Yeah, you can see the presentation. Okay.
I should wait until 11:20.
Yeah.
Okay.
Because maybe there are other people that wants to hear your presentation. So
yes, I'm sure there will be a ton of people just to hear me.
Why not?
Exactly.
Yeah.
I hope Zoom doesn't crash with the sudden influx of hundreds of people.
It's behaving well, so I think so. Okay. There won't be any problem. Okay. So don't forget, in the afternoon we have the other session. Okay. So be there at 3 p.m. Okay.
It's also for undergraduate students that published already a paper, and so it will be interesting also to see you there.
Okay.
Can I start?
Yeah, Rodrigo.
Okay.
Yeah.
Thank you. So the title is Limits of Sequences of Pedal Triangles.
Sorry, I didn't said the title. Yeah, Limits of Sequence of Pedal. Okay.
No problem. So first of all, what is a pedal triangle? So we take an arbitrary triangle, we project the vertices onto their respective opposite sides, and joining those three projections, we get a new triangle, which we call the pedal. So over here is an example of the pedal of an acute triangle. The pedal of a so the pedal is in brown. I forgot to mention that of an obtuse triangle. And here is the pedal of a right triangle. So in this case, two of the projections will actually coincide, And so we our triangle degenerates into a segment. But if that doesn't happen, we can keep repeating this process. So we create the pedal, and then the pedal of the pedal, and so on. And at least in this example, there seems to be some sort of convergence. And it turns out that the convergence always happens, and we actually have a formula for the limit point. If we consider our vertices as points in the unit circle of the complex plane, the limit point will be described by this formula. It's not very pretty, but it's nice that we have it. And so what we'll do now is we'll fix two of the parameters of the formula and let the other one vary. And this corresponds to fixing two of the vertices of our triangle and letting the other one go around its circumcircle. And so, and I can try and show you that what is happening. So I hope everyone can see the video. So two of the vertices are fixed. The other one is going around, and the limit point is tracing some sort of path on the plane, as we can see in red. So back to the presentation. So then the shape of these curves will only depend on the length of the chord between the two fixed points, and we can actually describe the whole family of curves by fixing one of the fixed points and letting the other one go around the upper half of the circumference. And so again, I'd like to show you what all the curves look like. Like so. I hope everyone can see it. There it is. So one of the fixed points is fixed, and the other one is going around just the upper half of the circumference, and we can see all of the curves that can be obtained. And back to the presentation. All right, so most of the curves were pretty complicated, but there are actually some very simple ones which we can explore. So first of all we have the point. This happens when the two fixed points are in the same location. So we don't get a triangle, we always get a segment. And the pedal of the segment, we can see that it will the limit point will be exactly on the location of the two coinciding fixed points, and so it never leaves that location as the other point goes around the circle, and the curve we obtain is a single point. The other simple curve we can explore is when the two fixed points are opposite each other. And so the moving vertex, there will always be a right angle at the moving vertex. And so the pedal will first degenerate into a segment, which will degenerate into a point located at the moving vertex. And so the limit point always coincides with the moving point, and the curve we obtain will be the circumference. Another very simple curve to describe is the segment. This happens when the chord of the fixed points subtends an arc of amplitude pi/2. And so the pedal will be a right triangle with the right angle at the, well, I can show you. The pedal will be a right triangle, and the right angle will be in the line that contains the chord of the two fixed points. So here is an example. Here's another one. And here's one that shows that the right angle may not be at the chord, but it's always in the line that contains the chord. And so the limit point will be located exactly at this right angle. And the whole curve is obtained by projecting the circumference onto that line. And so the segment we obtain will have a length equal to the diameter of the circumference, which is 2. And here it is, the segment. Okay, you might have noticed in that video as well that there is, even though the curves look pretty complicated, there is actually a lot of symmetry. And so, first of all, we can see that the chord of the fixed points is an axis of symmetry, and this can be seen by noting that although the triangles themselves are not symmetric, their pedals will be symmetric with respect to this chord. So whatever happens in the top of the chord will be mirrored in the lower half. And an easier axis of symmetry to explain is the perpendicular bisector of the chord, because what's happening is when we reflect the moving points on this line, the whole triangle gets reflected, and so whatever happens in one side will be mirrored in the other. So here are some examples just to show the variability of curves that we can obtain, but they all follow those symmetry rules. Okay, so last I want to talk a bit about the differentiability of these curves. So if we introduce the following two variables, B and C, defined as such, we can prove that if their sum is a rational number, which is a multiple of 3 divided by a power of 2, then the curve we see will be differentiable. This is actually quite easy to prove, we just plug in the values in that formula, and we see that from a certain point, the whole thing telescopes into a single term. And so we get a finite sum. That series that shows up in the formula will actually be a finite sum of differentiable functions. Therefore, the curve will also be differentiable. So here are some examples. At the top, there's that value of R. And so we can see that these curves look quite different from the previous ones. They're actually very nice and smooth. And what we can try is, let's remove that factor of 3 from the numerator of R and see what kind of curves we obtain. And we can see that they look very similar to the previous ones. They look very nice and smooth. And so there we should be able to explain why they look this nice. Maybe we can find some sort of proof. And there is a bit of a geometric explanation. So here we have, so if we call A the angle at the moving vertex, and A prime the angle of the corresponding pedal vertex, A prime can actually have 3 different expressions depending on the triangle. But pretty much because of this factor of 2 over here, we can deduce that if that value of R is of that form, so P, so just an integer over a power of 2, the nth pedal will be a right triangle. And as we saw with right triangles, the next iteration will be a segment, and then it will terminate at a point, which will be the limit point. And so the sequence will terminate in a finite number of steps. And so this might hint that we should be able to prove that the curve is differentiable without that factor of 3 in the numerator. And it turns out that we can, in a manner very similar to the previous one. We just plug in the values. We just have to be careful because there will be this extra exponential that will factor out. But then from a certain point, the series again telescopes into one single factor. And it all hinges on this value here that I call R cubed, which will be the remainder of this integer here when divided by 3. And so again, we obtain a finite sum, and the curve will indeed be differentiable. And just a little side note that we can actually recover the previous result if the numerator is a multiple of 3, then this RQ will be 0, and it will disappear, and we recover the previous expression. So that's it. Thank you all for your attention, and thank you to the professors for the invitation.
Okay, thank you, Rodrigo, for the interesting talk. Okay, questions? Comments? No?
Hi. Yeah, absolutely. Can you hear me?
Yeah, Chris.
Yes.
Yeah, you can ask. Yes. We see you. Okay, go.
That was really cool. It's really surprising to me when you said you're going to draw the curve of the limit of the pedal points. It's very surprising to see that most of the time it's not. It's like really strange and not differentiable. Do you have any reason for expecting that, for making that less surprising?
Well, actually, no. I was just as surprised when I started playing around with this limit point and seeing almost of a certain fractal nature. I think if you actually zoom in, I think you can actually see some sort of fractal behavior. But unfortunately, I didn't really get the chance to explore that. In Manning's article, he actually considers a different family of triangles, of just isosceles triangles, and is actually able to prove in that family that the curve is not differentiable. But unfortunately, I didn't get to that. But it does make for some very nice drawings, at least.
Yeah. Yeah, that looked like a really cool result. So it was really a big improvement over this paper in 2010, in the sense of having this proving it for other values of p, or for other yes.
Yes, I was very surprised at being able to do that, but again, it was just following Manning's idea of just plugging in and getting a telescoping series. So, yeah, and it had in my head there had to be a way to prove it because of that geometric insight of the sequence ending in a finite number of steps. So I was pretty glad to be able to find a way to actually prove it.
Did you study another, like the area of the triangles or other?
Yes, there was actually a lot of geometric things that we started to see, like angles, lengths, perimeters, and whatnot. But then I sort of stumbled upon these curves while studying this problem, and the professor that I was working with who also thought we should focus on this. She also thought that it was a very interesting thing.
And challenging.
So we focused more on this.
On this problem, no? Yeah.
Yes, exactly. Exactly.
It's better. Yeah. Okay. More questions? Or comments? Okay. So you are going to continue, no? With this.
Well, I definitely would like to maybe try and get a bit more insight. Maybe I'd really like to explore more maybe the fractal nature of these curves. They're very pretty, and so it would definitely be very interesting.
Perhaps there is an action, no? An action of a group there in the vertices, no?
Maybe we haven't really explored in that sense, but it's definitely a possibility.
Okay, so you could study that.
Exactly.
Okay, so I don't. Okay, there is no more questions. So thank you very much, Rodrigo.
Thank you.
So I think there is a question on the Q&A
yeah.
box.
Thank you, Elizabeth. I didn't see the.
Yes.
Michael Rothwell is asking, what software did you use to plot the curves?
Well, yes. When I was exploring this problem, I actually did a little applet on GeoGebra to be able to plot the limit point. But these images were made using MATLAB. I used that for that formula that I showed in the slides, and that's how I was able to plot the curves.
To see the what is the curve.
Yes.
Okay, thank you. More questions? No? Okay, so we thank again Rodrigo.
Thank you.
Thank you very much. Okay, so I think I'm going to pass to the last speaker of the morning. Okay, so we have Christopher Godinski. I don't know if I'm saying well your name. Sorry if it's not. Okay, so Christopher is from Universidade de Coimbra. Okay, and he's going to talk about a polynomial model for filling in incomplete data. Okay, can you tell us about your what are you doing? Okay, so you can start.
Yeah, so I did both my my undergrad and my master's degree. I'm in the last year of my master's degree at University of Coimbra.
You are you are in the Faculty of Sciences, so in the Maths department, no? Yeah, okay.
So my first research experience was my second year. I had the Godinski. But today I'm talking about my kind of second serious research experience, more or less serious, which was not the Godinski. It was a grant that we had at the university for master's students called the MobiWise project. So my presentation is about it's kind of data science-y. I'm going to be talking about a problem called collaborative filtering. And if you watch until the end, I have a little problem which might be low-hanging fruit for somebody who likes a computational.
Okay. So you can start if you want to share your presentation. Okay.
So let's say we have some sort of process that's generating vectors in Rm, which I'm drawing as column vectors of this matrix here. And this process generates a data set of n data points. So we have m times n coefficients here. We have all of these numbers, all these blue blocks, and the numbers that we observe. And now our process generates one last data point, so xn plus 1, but now we only observe a subset of the coordinates. The question we ask is, how do we infer? How can we figure out what that last missing coordinate is? Okay. call these variables here the independent variables. We call this variable the dependent variable. Basically, what we're trying to do is find a way to infer our dependent variable as a function of the independent variables using information that we were given. So this is what we call a regression problem. What's kind of the first approach to solving a regression problem? Well, maybe there's a linear model. Maybe there's a linear function that takes independent variables, which can approximate vectors of our data set. Our strategy is simply to find a linear function that fits the data we have observed and use it to compute this last missing coordinate. So this is the model of linear regression. Well, let's step back and let's make it a bit more complicated. Let's say we have a process, again, producing vectors in Rm, but now every data point we get from that process has some coordinates missing. You're never able to observe entire vectors. You can only observe some coordinates. Now, the problem of inferring missing coordinates is not really a regression problem at all. It's something we call a collaborative filtering problem. So there's a kind of classical example of collaborative filtering problems with build recommender systems. So let's say that we're Netflix. We have a collection of users and a collection of movies, for example. And let's say that every user movie, we're going to have some numerical value which tells us how much that user likes that particular movie. And let's say that for every user, we can observe or measure this value somehow, but only for a subset, for a small subset of movies. Okay, then we have the problem. How can we use this sort of data drawn from a very wide collection of users to try to predict how users will like movies that they haven't seen yet? So how in the world do we solve this problem? Well, if there's a very natural analogy of linear regression in the case of collaborative filtering, it would be something called a low-rank matrix completion. So what's the idea? The idea is to assume that maybe has some linear relations present on it, which is to say that this matrix, our data matrix, if we had these missing entries, would turn out to be a low-rank matrix. Then our strategy is to try to choose these missing values so that the rank of the matrix we get is minimized. And it can be argued that this is a good idea. If this matrix is low rank, if it has many columns, if we're observing enough entries, and if the entries we're observing are kind of generic in a precise sense, then yeah, matrix M will be recovered as the unique solution to this minimization problem. Only problem, there's a little problem, which is that low-rank matrix completion is pretty hard. So one of the attractive features of linear regression was that it's very easy to solve. A low-rank matrix completion is not easy to solve. There's no algorithm that, in general, we can just throw it on a problem and it'll efficiently compute the solution. But we do have a numerical method that seem to work in practical problems. So let's go back to regression for a moment. And let's say that we're looking at a data set and we want to infer this missing value, but by fitting some possibly nonlinear model. Well, if we have a space M of model functions, which is a linear space, and it's finite dimensional, then as you might know, the problem of fitting a model that agrees with the least square sense and using it to compute its missing coordinate is exactly the same as applying standard linear regression techniques to a transformed data set. Right? So what's the idea? If you're not familiar with this feature map idea, is, well, let's say that F1 to FR is a basis for M, right? And we're interested in solving this problem. We're trying to find a model from M that minimizes the sum of squared errors in our data. Well, if we write this model in coordinates and look at this minimization problem, well, this is just a linear regression problem on this data set. where our dependent or our independent vectors have been transformed by a certain feature map. So we can turn the problem of fitting a nonlinear one into the problem of just applying linear regression. So if you have a linear regression algorithm, we can solve this problem. Okay, if that made sense, then we have an idea, which is maybe we can apply the same trick to low-rank matrix completion. So let's say we have some data, and it doesn't have linear relations, but maybe it has non-linear relations present in it. And maybe we can choose a feature map, transform our data, apply LRMC there, and then use that completion to infer our data. So this idea was quite recently by a paper in 2018, edited last in 2020. And their proposal is to use, let's consider this feature map. So this is a feature map for homogeneous polynomials in 3 dimensions. Let's think of the case of 3 dimensions. So again, what's our plan? Let's say we have here. We know the coordinates y and z, but we don't know x. Well, when we apply it under our feature map, what coordinates do we know in our feature space? Well, we know y and z, we know y squared, and we know z squared, and we know yz. These coordinates we can't be sure about, but we definitely know these ones. So that's the plan. Let's take our data set, apply this transformation, apply low-rank matrix here, and then use the completions of the columns to impute these entries. And again, the idea of this approach, why this is interesting, is that quadratic relationships here turn into linear relationships here. So maybe this will let us impute and infer the missing coordinates in data from the hypothesis that it has quadratic relations. So, the moment of truth, does this work? And the answer is sometimes, and sometimes it fails. So actually, there are very specific conditions we can state under which LRMC will work, and there's a wide range of conditions where the problem should be well posed, but this method is not going to give us any useful results. Okay, so what's going on? So why is LRMC not working as well as we would like it to? Really, the problem that we'd like to solve, if we think about things from first principle, is we'd like to choose these entries of our matrix so that when we apply the feature map to the whole matrix with all the entries constrained, this transformed matrix has low rank. Right? So in terms of a minimization problem stated on the transformed matrix, we want to choose these column vectors so that this is minimized, and so that these constraints are satisfied. So for every column, we're going to have some blue vector in our original data that maps to this vector under our feature map, and that verifies those coordinate constraints. But that's not quite. This is not quite the problem that LRMC is solving. LRMC really turned out to be solving a relaxed problem. So that method I mentioned a while ago, it's solving a relaxation of this. So to give you an idea of what this relaxation is doing, let's look at one column. Let's say we have XYZ is a column of the original matrix, and we know that X is 1 and Y is 2, and this is the transformed column. So currently, we're telling the LRMC solver that A is 1, B is 4, and B is 2, right? Because A is X squared, B is Y squared, and D is XY. So we know these elements. But there are a bunch of other relationships. There are a bunch of other constraints that really this column ought to satisfy. The problem is that those constraints, you can state them, but they are quadratic constraints. And I don't really know of a good way of using those quadratic constraints in the LRMC solver, in the algorithm that we have for low-rank matrix computation. However, there turns out to be another linear equation we can use, which is E equals 2F, which we are not using, right? And why does this happen? Well, E is YZ. We know that Y is 2. This is 2Z. But x, well, x is 1, so this is 2xz. Okay, so we have this condition, and we weren't using it. Okay, so here's our idea. Maybe we can make LRMC work. Instead of just enforcing these k plus 1 choose 2 conditions on each column, or let's say that here I'm observing 2 k coordinates. In the corresponding column here, I was being able to tell you k plus 1 choose 2 coordinates. But with this that I've kind of alluded to, but not explained entirely in the previous slide, there turned out to be an extra k minus 1 times m minus k, a linear constraint active on this column. This is a pretty big number, because in practice, we assume that k is going to be a pretty big, pretty large, or k is, rather, m is going to be, and it's the number of dimensions we have here. The k is going to be pretty small, so this is going to be a big in practice. But we have a bunch of questions. So we've done experimental results, we've done computational experiments, and shown that this method seems to work really well. But we're lacking 2 things. We're lacking theoretical guarantees about how well this method works, about what kind of problems will become posed that were not previously well posed. And we're lacking some really good numerical experiments. So I'd like to be able to find an efficient solver for LRMC that can use constraints, right? Because previously, LRMC was minimizing the rank of this matrix subject to coordinate constraints. Right? Now I want to also apply affine constraints, or rather linear constraints on its columns. And this requires a little bit of change in how the algorithm works, because it's using some very special features. Anyway, but it seems like a pretty promising direction. It seems like it should be possible to write an LRMC type algorithm that uses this new methodology. And this might help you solve some collaborative filtering problems in the wild. It's pretty exciting. Unfortunately, I'm this right now. I haven't had any time to work on this. So if anybody would like to contact me, that'd be great.
Yeah. Okay.
That's my presentation.
Okay. Thank you very much, Chris. Okay.
Thank you.
Okay. So is there any questions to Chris or comments? So if you want to contact him, there is the...
Okay. It might be easy to do this. It'd be really cool.
Okay. There is...
I think an attendee is raising a hand.
There is a question, no? Margarida, I don't know if... Margarida, I don't know if she can...
I think she can.
To put the... Luis. Margarida can ask the question? Or?
Yes, of course.
Margarida, if you can... but she's not able to speak, or
I'm going to see.
Otherwise, she can write.
Yeah. Margarida, can you write the question, or is
no?
Okay.
You can speak
now. You can talk now. You can talk now.
Margarida, you go on.
Are you listening? Can you hear me? Yes.
Loud and clear.
Thank you very much. First, I would like to congratulate the organizers and the participants for these interesting talks, and it's interesting initiative for students to present their works. About the Christopher talk, I would like to, I think it's important to mention that Christopher is a master student, but he's preparing his master thesis in a different subject of the one that he told you, was talking about here. in parallel, he has been involved in this project, working in this problem with Professor João Gouveia. Not with I'm the supervisor for the thesis, but I'm not the author of his thesis, but I'm not the person who is supervising this work that he was doing here. But I think there are some relations between the work he was doing and the background that he has been developed in differential manifolds. And I would like to that it would be interesting it would be interesting if you could say something about that. If there are some relations that could be explored that you could explore in future.
Yeah, yes, Margarita Camarena is my thesis advisor for the master's degree, and it's a totally different subject from this. This is really just I have a kind of tentative interest in data science.
What is the subject, Chris?
Differential geometry and control theory.
Ah, okay, okay. Mm-hmm.
As far as things, the mathematical background that this shares with my differential geometry studies, I'm kind of I don't know if I can think of anything in particular. That I mean, there's lots of connections in mathematics. That's kind of the name of the game.
Yes, but what I was expecting to see is some application of the work that have been done in this project with image analysis or something.
In what was that? In application in what? I didn't hear.
Image analysis. If you have an image and you can you don't have a very good resolution of the image, if it's possible to use this kind of nets to
yeah, definitely. I mean, kind of from a very general standpoint, the problem of improving the resolution of images
yes.
is a collaborative filtering problem, right? You have images, this diagram. You have here are images, here are the pixels, and you have lots and lots of images, and you have lots and lots of pixels. I don't think it could apply to that very easily unless you take very small images. But it's definitely a collaborative filtering problem in this kind of methods that look for latent factors, that try to infer latent factors from a data set that looks like this, definitely are being used in algorithms, the kind of algorithms we have to improve resolution. But as I said, this particular method I'm using now, I'm still looking for algorithms to see whether we can really do this in practice. Another thing I definitely don't have time to talk about is that, you know, if you do linear regression on a feature space, you oftentimes don't actually apply this map. You use a kernelized representation. A similar type of trick could be very useful for this lifted lower income matrix completion idea. So using a kernelized representation of the problem statement, a possible way that makes this kind of method applicable to those very high dimensional problems.
Okay, very interesting. Thank you very much, Christopher.
Thank you, Margarida, also for your contribution.
Thank you. Just to, Anna, if I may, just to like to congratulate all the students and mention that there were already some feedback regarding this parallel session. Mentioned that it's very high standard quality, and so you are we must congratulate all of you for your work and your contribution, right, Margarita? Right, Anna?
Yeah, very important contribution, yes, to this meeting. Okay, and thank you very much all all the speakers, okay, for being here. Okay, it was a pleasure, and I hope you can continue to go to the other talks. Okay, I think it would be good for you to listen to the other speakers also. Okay, and good luck for your future. Okay, and we see you soon. No, in another in another
Thank
time.
you very much for the organization. It was very good.
Okay, thank you.
Thank you, Jan, and also thank you, Jan, for starting this movement, because it is the first time that the students are able to contribute in this way in this such important event in Portugal, and so now this is an international event, and so Jan was wanted to participate, and there was no opportunity
trigger to the
for undergraduates, and so thanks to this initiative, we were able to organize this, and we are sorry that many other students that we during this organization, we found out that there's other colleagues that wanted to join, and it was not possible. But next year, next edition, we might have some more opportunities for all of you.
Okay, and hope to see you in the afternoon. Don't forget at 3. Okay. Okay.
Thank you.
Okay.
Thank you so much.
So see you next.
Bye-bye.